All right, I have a video for everyone on limiting reactant, excess reactant, and percent yield. So you can just take some notes on your own sheet of paper for this one. All right, so here's a little question for us. If I have 3 moles of N2 and 4 moles of H2, which reactant will limit? I'm not really sure about that. I mean, I saw limiting reactant a little bit over spring break, but let's just kind of try to solve this BCA table and then answer the question. So I have 3 moles of N2, 4 moles of H2, and I'll have no product to start because we haven't actually mixed any of the chemicals before. We're going to go do our change, minus 1x minus 3x. Remember, these get minus signs because we're using up the reactants, and the 1 comes from the balanced equation and the 3. And on the product side, we're making this product, so it gets a plus sign, plus 2x. So now, kind of off to the side somewhere, we need to find what x is. So if I look, I'm going to do this for both reactants. So starting with N2, I'm going to take the before, 3 moles, divided by the coefficient. So that's 3. And I'm going to do the same for H2. So I take 4 moles divided by the coefficient of 3. And that gets me 1.33. Before, when we did this, 1 was always excess, so we knew that was bigger. But now I just have 2 numbers to compare, nothing really different, right? So if I look at these numbers, one of them is much smaller. This guy is smaller. So that means it's going to be my x. So the x is the smallest of those values. And the chemical that gave me the x is my superstar. So in this one, H2 is my superstar. So now it's all about the superstar. So minus 1, minus 3, plus 2. And we're going to plug that same x value in for everybody. Because once we figure out the superstar, it's like the favorite sibling in your household. It's all about the superstar. So now I'm going to do, figure out my A, and remember B plus C is how we get our A box. So I'm going to take 3 minus 1 times 1.33, and that gives me 1.67 moles of N2 remaining. I'm going to take 4 minus 3 times 1.33, and that gives me 0.01. And I just know that this was a repeating, and that's a rounding issue. My superstar should always end at 0. So just because of rounding is why I got 0.01. But the reality is, if I hadn't rounded this number, I would get 0 moles of H2 remaining. And then I'm going to take 0 plus 2 times 1.33, and that gives me 2.66 moles of NH3, and I'm going to use the word produced here because it's not that it's remaining, it's what we actually made. So which one will limit? Which one is determining who, like how much of this product I can make? Essentially, who runs out first? Well, looking at my after, the one that runs out first is H2. So H2 is called the limiting reactant. It's the superstar, it's the one that ran out first. So I'm going to go back. The excess reactant is the one that we have leftovers of. So I'm not talking about products, I'm only looking at reactants. So this is my excess reactant. And how much of it do I have? Reactant. I have 1.67 moles of it remaining. We can look back, NH3 is our product, and we will make 2.66 moles of NH3. So this is the beauty of the BCA table. We were able to answer 3 questions. Who's the limiting, who's excess, and how much remains of the excess, and how much product are we able to produce just by doing the table one time. Same question, just on a different slide, how much excess will remain? And finally, how much NH3 will be produced? So here's some vocab. The limiting reactant is the one that determines how much product we can make, meaning it runs out first. So I cannot make any more of my NH3 product because I ran out of hydrogen. You can't make NH3 without H, right? So we call it the superstar, but one good quality of the limiting reactant to look out for is that you will always have 0 moles in the after box of the BCA table. The excess reactant, notice both of these are reactants. This is the reactant that does not limit how much we can make. There's extra of it or excess. So you will always have either the word excess in the box after or a number. In the case of today, we're going to have numbers. We want to know exactly how much leftover will we have. Some of you may have wondered why the picture on Canvas for this unit is a hot dog. If I could change one useless thing about the world, right? There's lots I always rant about that I would change, especially in terms of naming things in chemistry. I want it to be named differently. But if I could pick one thing that really would make zero impact on anyone's lives, but is very important to me, it has to do with hot dogs, okay? It drives me nuts. If you go to the store, you buy a pack of hot dogs, there are 8 hot dogs in a pack. You go get buns, there are 10 buns in the package. That makes no sense, right? So I go to the store one week, I get a pack of buns, I get hot dogs. Great. I'm always left over with 2 buns in excess. And so now in my pantry, I have these stale buns sitting there, right? I don't want to throw them away because there's 2 of them. So what do? I go back to the store, get more hot dogs. But now I have extra hot dogs, right? I don't understand why hot dogs and buns don't match up, right? If I could change one trivial thing about the world, I would make 8 hot dogs, 8 buns, or 10 hot dogs and 10 buns, so that both of them were limiting and they ran out perfectly every time at the exact same time. That's why the picture for this unit is hot dogs. Okay, I want you to pause the video and try this one. It's got both reactants, starting amounts in moles, so pause for real, and then I will put up the final answer so you can check. All right, so I have moles of MgCl, let's get this guy, moles of MgCl2, moles of Na3PO4. I set up my BCA table, right, none and none, and then we do minus x's and the plus x's. In order to find x, that's this guy down here, we take the before divided by the coefficient. So 0.75 divided by 3, and the before divided by the coefficient. The smaller one gives me x, 0.25, and notice I plug that in for all of my x values, right? That makes this guy my superstar because he's the chemical that gave me x, and then we can just plug in and do B plus C to get A. So 0.75 minus 0.75 is 0, which is a good sign of our superstar, right? It should end at 0. 0.65 minus 0.5 is 0.15 excess remaining. 0 plus 1.5 is 1.5, and 0 plus plus 0.25 is 0.25. They want to know how many grams of NaCl should be produced. So in this mess over here, I was finding the molar mass of NaCl, 1 Na plus 1 chlorine, and that got me this 58.4. So sorry, that's kind of messy, but all I'm going to do now is the little mole island. I'm going to take my 1.5 moles and multiply it by the molar mass. And so what this means is if I mix 0.75 moles of MgCl2 and react it with 0.65 moles of Na3PO4, I should make 87.66 grams of NaCl. What you just found there is called the theoretical yield. Oops, I don't want that. I want this. 87.66 grams. So think of this as like, I'm picturing like a super nerdy TV character, like in theory, based off my calculations, we should have made 87.66 grams, right? We had to be nerds and use our calculators. We did a BCA table and stoichiometry to figure out, in theory, if I mix X and Y, how much product should I make? So picture yourself being extra nerdy, like I literally just pushed my glasses up my nose, super nerdy, that's the theoretical yield. Actual yield is how much you actually make in the lab. So usually this is going to be provided for you in the word problem, or you will actually do the lab yourself. So I snuck into Legend, even though it's locked down, and I actually mixed those 2 amounts of the reactants and made some product, and I actually in the lab collected. So I did the reaction, I separated the NaCl product, I let it dry, I put it on a balance, and it actually weighed 90.2 grams. So we have 90.2 as my actual and 87.66 as my theoretical, the calculated, what I should have gotten. There's a way to relate those. It's called the percent yield. We saw this once first semester in honors, but it's now more useful for us. It's comparing what we actually made in the lab to the theoretical yield, which is our stoichiometry or our BCA calculation. So we're going to take actual divided by theoretical times 100. So in our case, my actual yield, when I snuck into Legend in the lab, was 90.20 grams. My theoretical was what we calculated, 87.66 grams. We're going to times that by 100 to make it a percent, and I got 102.9% yield. Interesting. That means I made more than I was supposed to. Well, when we have a percent yield higher than 100, right, That means whatever I made in the lab weighed more than it was supposed to. What are some reasons this could happen? Well, a lot of times we have to let a product sit overnight to dry. Is it possible that all the water or the aqueous didn't evaporate off of it and so it's still a little wet? That would make the mass on top higher than it should be. Or maybe I left it and it got contaminated, that now there's some dirt or something else in there, right? So those are some reasons why we might have a percent yield over 100. Under 100%, right? So I made less, usually has to do with transferring. So maybe I transferred my reaction from the beaker to the balance, right? I was scraping it out of the beaker to put it on the balance to weigh. Is it possible that a tiny, tiny particle was left behind, or many, many particles were left behind, stuck to the beaker? Absolutely, and that would result in the actual yield on top being lower maybe than it should be, so we would get less than 100% yield. So just some things to think about in lab of why we might get something over 100 or under 100, and usually they're out of our control, but we do need to think about them. All right, this one's along stoichiometry, so it says if you actually make, it doesn't say the word actually, I notice I'm entering, if you actually make 46.8 grams of calcium carbonate by reacting 87.5 grams of CaNO3 with plenty of Na2CO3, what is your percent yield? So we have actual to do actual divided by theoretical, but now we need theoretical yield. So let's turn this grams of CaNO3 into moles. Right? Plenty to me means excess. So I'm going to give you some time, pause the video, do your BCA table, and then we'll talk about how to use your answer for percent yield. All right, so first thing I did was turn my provided grams into moles for my BCA table right there, and then I have excess and 0 and 0. I do my minus x's and my plus x's. Notice I needed to balance, so there's a 2x there. And then I need to find x. So I'm going to take 0.53 moles divided by 1, because that's the coefficient, and then for Na2CO3, excess divided by 1. Obviously, the smaller one is 0.533, so that's what I plugged in for all of my values. B plus C equals A, so I got 0, excess 0.533, and 1.066 moles. How do I know what my question mark is? Well, we want the percent yield of whatever they gave us as the actual yield, calcium carbonate, which is this guy. So I want to know, in theory, based off my stoichiometry, how much calcium carbonate should we make? So down at the bottom, you can see I took my 0.533 from right here, and I'm just going to use the molar mass of calcium carbonate and mole island. So in theory, my theoretical yield of calcium carbonate is 53.35 grams. Notice, we still have not touched this number up here, 46.8. Right? It's still sitting right there, haven't used it at all. Right now, I'm going to take actual, 46.8, divided by my theoretical, 53.55, times that bad boy by 100, and we have an 87.7% yield. Less than 100, which means we somehow did not either make as much CaCO3 as we said we would, or we did make it, and some of it was lost in the transferring from the beaker to the balance. All right, do me a favor and take out the limiting reactant POGL that you worked on over spring break. It's the one where it started with Model 1 baking, and they talked about the recipe for the cake. So take that guy out. And we're going to start, actually this says number 3, but we're actually going to start by looking at Model 2. So flip to Model 2. Here's what Model 2 looks like. And I'm going to draw a picture here. There were some questions that go with it, but essentially I'm going to figure all of this out based off the picture. So I see that the chemical reaction is hydrogen, H2, plus O2, making H2O. So I have hydrogens in here, and let's count. 1, 2, 3, 4, 5, 6. I have 7 moles, we'll say, of those H2 molecules. And I have 1, 2, 3 moles of the O2 molecule. So now here's what we're going to do. We're just going to make some waters. And I know water has 1 of these black circles, the oxygen, and 2 of the hydrogens. So there's 1 water, right? I use this 1 black particle and both of those open circles. Same here. There's another one, and I'm going to just keep doing this until I run out of something. So what I've done now is I've made 6 H2Os, right? 6 H2O molecules by reacting those. And is there anything left over? Well, yes, I did not use this guy. So it looks like we have excess. We have 1 mole of the H2 left over. Okay, I'm going to show you how this relates to that next page, which I personally think is set up very confusing. Different. So on this page, what we just drew was called beaker Q. Would you agree that we had 7 H2s before and 3 O2s, and then we made 6 waters? If you look back, the limiting reactant was oxygen. That's the one that ran out, and there's 0 oxygen left over in my after picture. And the one that was in excess was H2, and there was 1 H2 left over. So for R, it says we're going to start with 8 and 3. So let's go. We said that there were 6 moles of water produced. My limiting was oxygen, and there was 0 left over of oxygen. Hydrogen was my excess, and there were 2 moles of hydrogen in excess. Let's do letter S, 10 and 5. So moles of water produced, we made 10. Limiting, we'll say O2 and H2, and there's 0 moles of both. Excess, we didn't have any, and so there's no leftover. So now, hopefully, if you were confused over spring break, you should be able to do these, and then you should be able to do the last page of the table, which is just last page of the POGL, which is just generic practice. So here's that same drawing again. So again, we started with 7. And 1, 2, 3, 4, 5, yep, and 3 of the blue, and there are no waters in my before picture. So, table, back, this line, what we did when we crossed everything out is we came up with the fact that we made 6 waters, right, and there was 1 excess hydrogen. Let's see if the BCA table also proves that. So, minus 2x, minus 1x, plus 2x. Find my x. So for H2, I'm going to take 7 moles divided by 2, which is 3.5. For my O2, I'm going to take 3 divided by 1, which is 3. So that is my X. Oxygen is my superstar. Minus 2 times 3, minus 1 times 3, plus 2 times 3. 7 minus 6 is 1 mole. 3 minus 3 is 0 mole. 0 plus 6 is 6 moles. Would we agree that in our after we had 6 moles of water, no oxygen, and 1 extra mole of my excess H2? So that's kind of a nice relationship between a particle picture like this, a before and after particle drawing, and a BCA table, right? Obviously, we don't have time to make drawings like this for every single problem, but it can be helpful when you're kind of figuring out what the BCA table means. Back at that. So I have another picture, and it says R. So I need, I drew, I believe, you can double check me, but 8 moles of the H2, 3 moles of the O2, and no moles of H2O. Now, if I do my cross-offs, right, cross off, and I do that until I can't do it anymore and pretend I'm drawing waters as we go, right, I should have something that looks like this. So let's do our BCA table to confirm. Minus 2x minus 1x plus 2x. Find my x down here. We take 8 divided by 2. That's 4. Sorry, that was my H2. And my O2 is 3 divided by 1. That's 3. So he's still x, and my superstar, minus 2 times 3 minus 1 times 3 plus 2, plus 2 times 3. So that gives me 8 minus 6 is 2 moles. 3 minus 3 is 0 moles. And 0 plus 6 is 6 moles. Is it true that I made 6 moles of water and 2 excess left over of my hydrogen? Yes. So here's how we relate that to the table. We will do rest. So we said 10 moles, 5 moles. In my before picture, I don't have any waters. Finish the rest or check the. So now let's do our BCA, minus 2x minus 1x plus 2x. Find x down here. We get 10 for H2, 10 divided by 2 is 5. For O2, 5 divided by 1 is 5. Oh no, they're the same. Which one do I pick? Honestly, it doesn't matter. They're both 5, so we can say these are both superstars. X equals 5. Minus 2 times 5 minus 1 times 5 plus 2 times 5. So 10 minus 10 is 0. 5 minus 5 is 0. 0 plus 10 is 10. So we made 10 waters, and there's no excess left over. This is the dream, people. This is the situation where hot dogs and buns run out at the same time. I have no leftovers, right? So back to the table. If it helps you for those last two, feel free to set up a drawing, just like I did with the beakers. That might be helpful or a good way to check your answer. So there's T and there's U that you are able to use, or you can just do the BCA table. Hopefully this was helpful.